Hi, I'm Zor. Welcome to Unizor Education. We continue talking about Lagrangian, and this lecture will be about Lagrangian in n-dimensional Cartesian space. So basically, we have addressed Lagrangian in some very simple case when we were talking about just an object on a spring, and we have proven that in this particular case, Lagrangian mechanics using the Euler-Lagrange equation is equivalent to Newtonian mechanics with second Newton's law. And today we will try to expand it to n-dimensional case. Okay, now this lecture is part of the course called Physics Plus for all. It's presented on Unizor.com, and I do suggest you to watch this lecture as part of the course on Unizor.com. It's a totally free website without any advertisement, without the need for subscription or anything like that, totally free. Now, all the material is presented in certain logical sequence, and that's why it's important to take this lecture as part of the whole course. Now, the whole course Physics Plus contains certain chapters, and this lecture is part of the chapter which is dedicated to Lagrangians and Hamiltonians. So before this chapter, there are some other chapters related to Newtonian mechanics which we will definitely use. So that's why you might actually consider the whole course, starting from the first lecture in this course, which is the first chapter of this course, which is basically laws of Newton, refreshed, readdressed, etc. Okay. So, what do we have? First of all, let me start from one-dimensional case and just recall that this is the equation for second law of Newton, and this equation d per dt dl or dx prime equals dl or dx. Now a is actually second derivative of x. This is a function of t, of course. So L is Lagrangian, which is basically kinetic minus potential energy of, in this particular case it was about a spring, object on a spring. So this is the kinetic minus potential energy of the spring. Now we will expand it to n-dimensional case. Okay. So let's start with this Newtonian equation, and we will try to expand this into n-dimensional case, and then gradually replace the force and the acceleration with their representation as part of the kinetic and potential energy. Basically, force is related to potential energy, acceleration is related to kinetic energy, and both of them will lead us to this particular equation. So that's the plan. Okay, so let's start with the force. Now, we do assume that we are talking about only conservative forces. So we have an isolated system of n objects. It's isolated in the terms, in the sense that there is no other external forces acting on objects within this system. They are only acting among themselves, using conservative forces like gravitation, electrostatic forces, the spring forces. The perfect model is our solar system. So you consider every planet as a point mass of certain mass, and including sun, of course, and they are gravitating to each other, basically exerting certain force. So any particular planet has force from all other sides. Well, the whole thing actually with Newtonian mechanics makes it a little difficult because all these forces are vectors in three-dimensional case, and their interaction is not really that clear. It's kind of complicated. Lagrangian gives you the ability to approach it simpler. Okay. although it looks maybe more difficult than this one, in reality it's a simpler equation, simply to obtain this equation. All right, so we have n objects. Now, every object has certain position in a three-dimensional case. So we will call it vector r, and it depends obviously on time, so all objects are moving, and this is their position, which can be described as xi of t, yi of t, and zi of t. So this is the vector. Now, similarly, the velocity is the first derivative of this vector, which is basically derivative of components, coordinates. And the second derivative, which is acceleration. So this is v, and this is I. Second derivative of t is second derivative of coordinates. Okay. Now, so that's position, velocity, and acceleration. Now, let's talk about the force. Let's assume that the force Fi, which is a vector, now it's a stationary force, like gravitation, for example. It depends only on position on all these other objects in the system. They gravitate, basically, in case of gravitation, and each one exerts certain force, and the force is basically depends only on position of two objects which are gravitating to each other, right? So we can say that every Fi, which is the combined force of the whole system acting on that particular object number I, it depends on position of all vectors. R1, R2, R3, Rn. Or, if you wish, it's a position of all coordinates from x1 to zn. Right? Okay. So, just for brevity, I will probably omit the arguments and just use Fi as a vector. Now, at the same time, we can say that vector has components. So it's Fix, Fiy, and Fiz. So these are three components by x, y, and z of the vector f. So these are three scalars, and this is the vector. Okay, now let's assume that position of the object number I is moving from position Ri to position Ri plus dRi. So certain infinitesimal amount of time passed and position is moved. What is the work which basically has been done by the field to move this particular object from this position to this? Well, infinitesimal amount of work in this particular case is equal to scalar product of vector of force and vector of displacement. So this is the definition of the work. This is the vector of displacement, this is the vector of force. Their scalar product gives you the work performed by this force, which moves the object by this displacement. Both are vectors, it's scalar product, and in coordinate form it's Fix times dxi plus Fiy components by dyi plus Fiz times dzi. So this is amount of work performed by this force. Now, okay, great. Now we have the conservation of energy law. So if somebody performs, the field actually performs certain amount of work, then the potential energy of this object will diminish by this exactly amount. So there's some new work and new increment of work and increment of potential energy must be constant. And that's exactly what we have. One is increasing, another is decreasing. So work, increase of work plus decrease of potential is zero, potential energy. Okay, great. But from this very easily follows the following. Now, if you look at this, you easily see that dui by dxi is equal to fxi, or ix actually, I use ix. And dui by dyi is fiy, and dui by d zi is equal to fiz. I think I need a new marker. Okay. So this is just a differential. It's pure calculus without any problems. The only thing which I'm missing is the sign. I need sign minus, minus, and minus, right? Okay. Now, just a little detail in this particular case. The sum of these, if I will take sum of dwi, gives me the total amount of work the whole system is doing, moving its own objects, right? And it's equal to sum of aix times dxi plus etc. y and z, and it's equal to minus d total potential energy of an entire system, right? If I would just summarize this. So it would be a total amount of potential energy. But now if you will look at this, you will see that f1x, for example, occurs only with dx1. f17y occurs only with y17. So what I can say is that the same fix is equal to minus du entire energy, not just ui, energy of the potential energy of ith object, but entire system by dxi. And fiy is equal to minus du entire differential, partial differentiation of an entire potential energy by dyi, and correspondingly z is exactly the same. So I'm using exactly the same equations like these, but I'm not using ui, I'm using entire potential energy, not potential energy of one particular object. So that basically gives me an advantage of having one particular force acting on one particular object to be derived from the total potential energy of an entire system by partially differentiating by coordinates only of that particular object. So that's what's important. So basically I have expressed the force in terms of total potential energy of the system. Great. Now let's talk about acceleration. Okay. Now let's talk about acceleration. Acceleration is the second derivative of components of position, right? Okay, so kinetic energy is 1/2 mass, let's say kinetic energy of the ice object, of ice mass times ice acceleration. Acceleration, times v square, I square, which is, what is the square of the velocity? Well, you can consider it always as a scalar product of vector, first derivative of vectors of position by itself. So position derivative, which is velocity vector, and if you would multiply velocity vector as a scalar product by itself, you will have the absolute value of speed actually square, which is equal to 1/2 m of xi square derivative square plus y derivative square plus z derivative I square. From this follows very simply that dki by dxi is equal to, well, y and z are not counted because we are partially making the derivative only by x, by xi. So it's 1/2 times mass, a by the way, times 2xi square, and 2 and 2 will cancel each other, and that's what it is. Now, if we will take as a derivative of this by time, d by dt, we will have, it was velocity. Now, if you will derive the derivative by time, you will have the second derivative, which is MAI. Acceleration. So we have acceleration mx, I acceleration, second derivative, expressed in terms of in terms of kinetic energy of the ice object. Now, kinetic energy of ice object depends only on ice velocity. Now, sum of kinetic energies, sum of kinetic energies is basically a sum of this expression by I. But if you will do this partial derivative of the total kinetic energy, not the ice, you will have exactly the same, because the total kinetic energy will be sum of x1 square plus y square plus z1 square plus x2 derivative square plus y2 derivative square, etc., etc. And if you will partially differentiate by one particular parameter, that would be still the same parameter, because everything else will be with different indices. So derivation from ki by xi is by xi strich. Okay, prime. Yeah, I'm deriving by prime. So derivation by x prime i's is exactly the same whether you will differentiate the kinetic energy of that particular object or total kinetic energy. Again, I'm trying to convert everything into dependence on total kinetic energy and total potential energy, which I did because it's additive functions. Kinetic is additive function. So if you have an addition of the first, the second, etc. coordinates, and you differentiate only by first coordinates, only first coordinates will remain. So we have expressed this, and we have expressed this. But they are equal, right? This is the force, and this is the mass times acceleration. So we have the second law of Newton equating them to each other, which means these two expressions, this and this, or this, in this particular case, this by x, 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 they are equal to each other. So what do we have? Let me write it down. For x and y and z will be the same, basically. We will have an equation, d by dt, so differentiation by time, of partial differentiation by total kinetic energy by velocity of the of x component of the velocity of i's object is equal to minus partial derivative of the total potential energy by x coordinate of the same object. That's what we have. Great. Now let's just do very, very simple simplification, if you wish, of this formula. So it will be a little bit more elegant. Okay, how to make it more elegant? Let L is equal to K minus U. Total kinetic minus total potential energy of an entire system, and it's called, by the way, action. Okay, now, kinetic energy does not depend on the position, it depends only on components of the velocity. And potential energy doesn't depend on vector of velocity, it depends only on positions, because we are talking about conservative forces, etc. So potential energy depends on position, kinetic energy depends on velocity, which means from here follows that dl by dxi is the same as dk minus u by dxi, but k does not depend on position, only on velocity, which means it's the same as minus du by dxi. So this I can replace with dl by dxi. Now let's talk about this particular thing. If I will put component of velocity, x component of velocity of the i's object, now k depends on this, but u is not dependent on, it does not depend on velocity, it depends only on position. So that's the same thing as dk that's the same thing as dk by dx prime I. Okay, so instead of this I can put L. Same thing. And that's what I have now. This is a little bit more elegant because only one variable participates. It's purely artificial thing, and that just to make it a little bit prettier, if you wish. So this thing, which is called action or Lagrangian, satisfies this particular equation, which we have derived from Newtonian, second law of Newton. Now, obviously, all these transformations are reversible, and from this equation we can always get the f is equal to ma for i's coordinate, for x, for y, and for z coordinate of i's object. So we will have exactly the same system of equation, of an equation actually, which Newtonian second law gives us. So this is basically a proof of equivalency between Lagrangian mechanics and Newtonian mechanics for systems with conservative forces. Now, one more, as I would say, cherry on the cake. Let's just compare this thing which we have just derived with this. So instead of this, I will put minus equals 0, which is exactly the same thing, right? Now, what is this? Let's think about Lagrangian. Lagrangian, it's a kinetic energy minus potential energy, which is a function of all positions and all velocities. Where I is from 1 to n. So it's 6n parameters. Each one of them depends on time. So basically, ultimately, it's a function of time. Because as time changes, position is changing and velocities are changing. So now consider this particular, from time 1 to time 2, integral of this function. What is minimizing or maximizing? What gives the extreme value of this functional? It's a functional because it's a numerical function of a function. L of t is a function. So function of function is functional. So whenever we want to minimize or maximize or whatever, we have Euler-Lagrange formula. And how does it look like? Well, it looks exactly like this. If you will go to a chapter called Variation there is one on Unizor.com as well, you will see that that's exactly what it is. That's Euler-Lagrange equation, which is a necessary condition for having this integral as at extremum. So the solution to this integral basically is the solution minimizing or maximizing this integral is the solution to this differential equation. Or in our case of n objects, it's a system of n different of 3n actually, because x, y, and z. So it's 3n different differential equations. Now the solution to this, which is x and y and z as function of t, is a trajectory. So trajectory along which the system of n objects is moving in this 3n dimensional space is the one which gives this particular integral or action, if you wish, extremum. So action is basically like a criteria, if you wish, minimizing, usually it's minimizing. So minimizing action in terms of solution to this system of differential equations gives you the trajectory, x and y and z for each object, I, xi of t, yi of t, and zi of t, gives you trajectory. So basically that's the kind of, I don't know, philosophical theory behind the whole thing. So action is a very important thing. Basically like a universal law of physics. If you would like to find out what is a trajectory, you have to minimize, usually it's minimization or maximize the action. And the action is difference between kinetic and minimize integral of action, because that's what actually gives you the entire action. Minimization of this integral gives you the trajectory, because minimization means solution to this Euler-Lagrange equation, and Euler-Lagrange equation is equivalent to Newtonian mechanics. It just seems to be a little bit more universal, if you wish. And now, by the way, as an example, in one of the previous lectures, there is a problem which I was solving using the Lagrangian mechanics, which is, for instance, for the object in a spring. Or then I was actually, I had another problem solved in the next lecture. It's a pendulum spring. Whenever there is a pendulum, but the pendulum is actually a spring, it goes up and down, and rocking left and right. So I solved that problem using the Lagrangian because it's kind of simpler to use the total energy rather than individual vectors. Now, the only thing is, in that second example, I was not using Cartesian coordinates. I was using the angle of rocking the thing and the displacement of a spring. It's not exactly Cartesian coordinates, but this is the subject of the next lecture, when I will talk about using non-Cartesian coordinates to basically use Euler-Lagrange equation with non-Cartesian coordinates, like in the case of pendulum spring. Okay, that's it for today. I do suggest you to read notes for this lecture. Every lecture has notes, and this one you go to unizor.com, you go to Physics Plus course, and you find their Lagrangian part, and in the Lagrangian part, this one is called Lagrangian for n-dimensional case. That's it for today. Thank you very much, and good luck.